Good morning, everyone, and welcome to the second part of the FunShield4Med learning module about computational methods in toxicology. The hands-on we will present today is about an already published study, which is reported here in the slide, entitled A Computational Understanding of Inter-Individual Variability in CYP2D6 Activity to Investigate the Impact of Missense Mutations on Ochratoxin A Metabolism. So the question we wanted to answer was, may CYP2D6 polymorphisms impact the conversion of ochratoxin A to its 4-hydroxylated derivative? This is interesting since this derivative is less toxic than ochratoxin A itself and can be formed by CYP2D6. The hypothesis we started with is that the metabolic fate of molecules can be predicted monitoring the arrangement of atoms undergoing the reaction to the catalytic core of cytochromes. So here in the slide, we have bufuralol, which is a known CYP2D6 substrate, and here is reported with the star, which is the part undergoing the hydroxylation. And as we can see from the movie we have in the bottom right of the slide, we can see how that part is kept close along the molecular dynamics simulation to the catalytic iron. And so to do so, to perform a molecular modeling study, what we need at first is a protein structure. To check for a protein structure, we go to the UNIPR database, which is, let's say, the most comprehensive database about protein sequences and also protein structure being cross-linked to other databases. So we start typing CYP2D6, which is the protein we are interested in. And as we can see, the first result we have is CYP2D6 within Homo sapiens, so the one we are actually interested in. So we open that entry, and we have now some information about that protein and that gene. So we have the function, we have names, we have the reaction it catalyzes, the subcellular location, some diseases, some variants, and also the variants that are interesting for this study. But what we are interested in now is if there are any 3D structure and crystallographic structure available. And as we can see, they are actually available. There are lots of them. And all these structures are stored, so we can open like this one. They are stored on the protein data bank. The protein data bank is the other gold benchmark database for protein 3D structure. And as we can see here, we have our human CYP2D6 with already bound some ligands. So we can open the structure, we can browse the structure from directly from the web. But what we are going to do actually later on is that we are going to download the structure on our local machine. Then the other thing we need to proceed with the molecular modeling studies is the ligand, the 3D structure of the ligand that we are interested in. And to do so, we will go on PubChem, which, as reported here, contains more than 100 million compounds. And we start browsing for ochratoxin A. So ochratoxin A, here it is. Also here we have some information about the chemical safety, the formula, the weight, a brief description, but most importantly, we have the 3D structure. So we can download the 3D structure in the SDF format. We already downloaded it, and we can save it, okay? Now, we can visualize this structure on Pymol, which is our visualization software that we use routinely. And so we can open it and visualize it. Now, with Pymol, we can also download protein structure using the fetch command. So we can download the one we see here, so 3TVG. To do so, we simply type fetch followed by the PDB ID, so 3TVG. And here you go. We have the protein 3D structure. As you can see, there are lots of red dots, which are water we need to remove, and also all the co-crystallized ligands and molecules needs to be removed. to then proceed with the molecular modeling study. We already did it, so we have already the protein ready to be used for the following docking procedure. And here it is. This is our protein cleaned and ready to be used for the docking procedure. So to proceed with docking, there are lots of different software we can use. We usually use GOLD, which is a GOLD benchmark for protein ligand docking studies. To use GOLD, we need to have a gold.conf file, which is a file that we give to our software as input that tells to the software which are the parameters to set and which are the protein to work with and the ligands to work with. So now I will show you the one we used for this study, for this hands-on. And the most important information we need to give to the gold.conf file is the origin, so the centroid, so where we want to dock our ligand, the radius within we want to dock the ligand. So starting from the origin, we use a sphere of 10 angstrom of radius, the ligand data file, which is ochratoxin A, and the number of poses we want the software to try. So we can put 10, we can put 100, we can put 1. And so he'll go for 10 tries, 100 tries, and the most tries we use, the most computationally expensive is, and so usually we stick to 10, from 10 to 20. And then the directory where we want to save our results, and most importantly, the protein data file, so the protein we need to use for the docking procedure. Then to run the GOLD docking procedure, we just need to use this command from the command line, which is called GOLD auto, followed by the name of the GOLD conf we already prepared. And then we press enter and the docking procedure starts. So we already did that, and the output is like this. So we have a lot of file. Actually, they are 10 file: GOLD solution number, ochratoxin A, M1, 10, 1, 2, 3, 4, 5, till 9, so from 1 to 10. And most interestingly, we have also a file which is called best ranking list, which tells us which is the the best pose GOLD recorded, which in our case is the GOLD solution number OTA 4. So this will be the best pose we will use for the following molecular dynamics studies. This procedure must be performed for every protein of interest and for every ligand of interest. So we can visualize it on PyMol, like prot, and we said the 4 is the best one. And here we go. So we have our ochratoxin A in complex with our CYP2D6. And interestingly, the portion near to the catalytic M is the one actually undergoing the 4-hydroxylation. And now that we have the docking results, we can start with the molecular dynamics simulation. And to do so, we use GROMACS. And this is a very long, let's say, procedure, since we need to use only the command line, and we need to perform a lot of steps, which are here reported. So we need to prepare the ligand, and we need to prepare the protein. Then we need to edit some files which are called topology files, which are files telling us all the information needed to perform a molecular dynamics simulation with our system. So the force field we are using, the proteins we are using, the ligand we are using, the type of water we are using, and so far and so on. Then basically what we need to do is to, once we build the complex, so protein plus ligand, we need to put it in a box, and we need to add the water in this box. Then we need to neutralize the system. And this means that we have a system with some charges. And what we do is add an equal name of sodium ions or chlorine ions to neutralize the charge we have. So if there are, for instance, we have a charge of +10, we will add 10 Cl ions. Then we minimize it energetically. We minimize also, we restrain the ligand, and then we proceed also with the part where we push our system towards a certain temperature, and then when we push our system toward a certain pressure. Usually we set 310 Kelvin and 1 bar of pressure. Then we can proceed with the actual molecular dynamics simulation. Once we obtained the molecular dynamics simulation, once it's finished, we need to clean the molecular dynamics simulation. And to do so, we use basically this command and followed by this one. So with the first one, we remove the eventual jumps that the molecular dynamics can create. And with the second one, we align all to the first frame so that we can visualize it easily. And to visualize the actual molecular dynamics simulation, we use VMD, which is a visualization software born to visualize molecular dynamics simulation movies. And so we type VMD followed by the name of the molecular dynamic simulation results, the file we just built, and it should get opened. It takes a bit because these files are quite heavy and the workload is all on the GPU. So it takes a bit. And also, hopefully you don't hear how my PC is, how high is going with the CPU and the fan. Okay. No, it should open. Okay. Here we go. So this is VMD. With this, we can move along the molecular dynamics simulation. With the graphical representation, we can visualize the protein in cartoon, which is easier for us. Instead, we can visualize the ligand and the heme in licorice. So here we go. And at this point, we can put on top this. Then we can smooth the trajectory so that we can visualize it better. And here we go. This is our dynamics, just cleaned and obtained with the procedure we just said. Then we can press play and it should start moving. Okay, it's a bit, okay. And here we go. As we can see, all along the dynamic simulation, the part that should be kept close to the heme and to the iron specifically, it's actually it's being kept close to it. So the same procedure we just saw for CYP2D6, which is reported here with 1, so the wild type CYP2D6, can be done with also its variants. And we can see here the results. So as we can see, CYP2D6 in the wild type, we have the yellow atom, which is kept close, which is the one undergoing the reaction, which is kept close to the iron of the heme within this CYP2D6. In these variants, we can see how far it is, and so we can assume, and we assumed that this variant is, let's say, it's not going to produce the 4-hydroxylated ochratoxin A, or at least it's not going to transform it in a way which is less relevant with respect to the wild type. And instead, in CYP2D6 110, we can see how close this yellow atom, so the reacting atom, is kept. Also meaning that this mutation, so subjects bearing this mutation, might be more prone, maybe, or prone as much as the wild type bearing subjects to transform ochratoxin A to its 4-hydroxylated derivative, so a less toxic metabolite. And for the hands-on, that's it. Hopefully, you'll find it useful, and thanks for your attention.